Alright, hey everyone. So we're moving on to the glass board now. We've worked through the exercise and you've seen that radius of curvature that happens as this particle comes in through an electric field and then goes through a magnetic field, and it creates this gyration motion. Now we're just going to work through the equations, and just see through the equations, see if we get the same value. But let me just slow it down and let's just draw out what our system is. Alright, and then let me draw our positively charged particle here, and it has some initial velocity just so it gets in between these plates, and then it gets accelerated due to the electric field, and it comes out to some at some point here, and then it begins feeling the effects of the magnetic field causing this motion. And so this is what the initial setup is here. We have a particle to begin with, and it has some initial velocity to make its way between these plates. It feels the effects of the electric field. Once it gets out of the plates, it no longer feels the electric field, so it has some final velocity, and now it's feeling the effects of these magnetic fields. And so how do we go about getting this radius here, as you saw at the end of your program? And so how do we calculate that? And so we need to think about forces. There's a force being felt due to these fields onto the particle. And at this point in time here, once we exit the effects of the electric field, it feels the effects of the magnetic field. And that's it. That's the only thing that's going on in our system when our particle enters this region where the magnetic field exists. So we know that for the net force of our system, thanks to Newton's second laws, should always come out to equal mass times acceleration. And as I was stating earlier, in this case, when you think of net force, that means adding up all the forces that are being acted upon, in our case for our problem, onto this particle. And in this case, we only have the magnetic field acting on it. And so we only need to know the force due to the magnitude of the force caused by that magnetic field. And I'll write it as F mag. And we know that F mag, when our positively charged particle in the presence of a magnetic field, is equal to Q V B. And so now we have a relationship. We can now let's write it out. We have mass times acceleration is equal to Q V B. Alright, so now we have a relationship of the forces, and now we need to think about the type of acceleration we got going on here. So if you've been following along and looking at our other YouTube videos, you've already seen when we did Project Mercury. And a big takeaway in Project Mercury is that when there's something in space, we'll just reference this particle, and it's moving at a curvature, its acceleration due to the centripetal force can be written as v squared over r. And this is the r we want, because that's the radius here. And so now we could plug that into our setup over here where mass times acceleration is equal to qvb, and we get mv squared over r is qvb. Perfect. Now we're able to solve for r, the radius, the gyro motion radius. And so to do some big math, we just want r, so we multiply r by both sides. We lose it here, and then now we have r over here, and now we want to get rid of these terms, so we divide it over qvb Alright, then we lose these. Now let me just clean that up. I'll move to the side. For here, we get mv squared qv b equal to r. And now it's like, alright, we could cancel some terms. There's a v on the bottom and there's two v's on top. So let's throw away that. And then we end up, I'm going to move r to the left side because we read left to right. mv over qb. So now we have our final equation, and this is following true to the laws of physics. All the logic is made to sense up to this point. And to now solve for it, we go back into our program and we look at the initial values that we gave for our particle. It's and this velocity here also to remember is we're looking at this moment in time when our particles enter the magnetic field and has just left the electric field. So this velocity here will be the final velocity that the particle has after it's traveled through the region where the electric field is. And then the charge of the particle, and then the strength of the magnetic field. And so if you go back into our program, to the program that you made, we have the elementary charge of the particle being 1 because it's positively charged. We have its mass 2. This could be something such as it's a proton and it has a neutron with it called the deuteron. We have a final velocity, or I'll just write it as VF, but this is just V. But I'm just doing this to reference this moment in time after the particle has left the electric field and has now entered the magnetic field. It's equal to 40. And then as well, we only care about magnitude, and so I know in your program the strength of the magnetic field might be a negative value, but since the magnitude is all that matters, we'll write it without the sign, which will be 0.9. That's something just to refer back to as you've been following all these videos. We're using different units than SI, which is typically what I work with, but this is just so it's not confusing. So Q is elementary charge rather than it being in coulombs, because in reality, for me, how I would work with it, this would be 1.6 times 10 to the minus 19 coulombs. And the mass is in atomic mass units rather than kilograms, and that would be really small because it's proton's really tiny. It's like 10 to the minus 19, I believe, kilograms. I might be incorrect, but it's really tiny. But this way, the math comes out a lot cleaner because we're still being true to the physics, and it's a lot easier to read as you work through the program and as we solve it here on the board. And so we have these values that were put into the program, and now we're able to solve what the true value of what this radius should be given the parameters in the physics that we've gone through. And this leads to a value of 88.89. And then I'm going to just highlight the emphasize here. This is the true value. This is what should happen given this scenario that we've set up here. And if you go back to the program and calculate what R is due to the simulation that you did, you get an observed value of 92.15. It is possible you may have something a little different, but if you do have a different value, all these calculations will follow the same. But yeah, I saw 92.15. And so now we want to calculate the percent error. How off were we from the true value? And so I'll just write this general form here. True minus observed. And in this case, we're just care about the absolute magnitude of these values, because this percent could be plus or minus, but we still get the same percentage error that we want to see to know how close we were over true and then to go to percentage, you throw in times 100. So you plug these in, then our true value over here. There we go. Nine. When you plug this in and you multiply it by 100, it comes out drawing approximately to 3.67%. Now this error is just pretty good, as we mentioned when you're working through the worksheet. We were expecting something, plus or minus 10%, and so getting something like this is just pretty good. We followed all the math, followed all the physics, and we found out that in the work that you did, you got pretty close to the true answer, it being off only by 3.67%.